Okay, so before I start, let me show you a quick demonstration. So let me start it a little bit late.
The greater the force, the more the current.
So here it's illustrating that when you bring a magnet
So if I
to
reduce
a coil, you induce a
linkage,
current. So this is the induced
the
EMF,
deflection will be reduced.
Faraday's law. Changing flux induces a current in the coil. So now look at the next
So
illustration.
if you want to depict the mutual inductance, let us consider two coils
He's going to illustrate
one
mutual inductance.
beside the other, and we will excite one coil with the help of this battery. So when we excite the battery, so there will be a current flow in the coil which induces an EMF in the secondary coil such that there will be a deflection.
So notice as he connects one coil to the battery, the second coil shows a change in the
So if
galvanometer.
I move further this coil, the deflection will be reduced due to the length of this. So if I reduce the distance, deflection will be more.
Okay, so this is
This is
here
how
the
mutual
situation.
inductance works.
The situation in this case, you have two coils. One is connected to a battery and a switch, so he's switching on and off, and the other one is connected to an ammeter or a galvanometer to measure the current. And as you induce, as he connects one to the battery, there is a magnetic flux that is changing, and the flux is also changing through the secondary coil, and you have an induced EMF and induced current in the secondary coil. This is what we call mutual inductance. So here we spoke about self-inductance in a circuit. We said if you turn on and off a circuit by a switch, the current that is flowing will induce an EMF because it changes the flux. The current generates a magnetic field through the loop, and this magnetic field is changing, so it will induce an EMF in the circuit. And we said that's self-induced EMF. Okay? Then we spoke about the, and we will speak today about the mutual inductance. So let me very quickly. So we said the induced EMF is minus L, the inductance, di dt, and we determined that for a coil of n turns, we can determine the inductance L, which is equal to the flux linkage, which is in this case the number of turns times the flux through a single turn, divided by the current, and we were able to derive later on that this is actually equal to mu 0 n squared times the volume, n where n is small n, number of turns per unit length. And it's also, you can also use this other equation. You can also use you can use also n, capital N, so it will be mu 0 capital N squared divided by L times A. A is the cross-sectional area. So you can see that the inductance is dependent on the geometry of the inductor, the length and the cross-sectional area, and is also dependent on the number of turns per unit length. Okay. Then we spoke about a circuit, and this is an LR circuit, and we said if you connect a battery to an inductor with a resistance in series, the current will increase exponentially, and it's given by epsilon over R times 1 minus exponential minus RT over L. So the time constant in this case is L over R, and it behaves very similar to the charge of a capacitor, charging a capacitor that we have seen before. Okay. We said also if then you connect the inductor to, so this is how the current changes when you are energizing the inductor. The current rises exponentially, the voltage through the resistor rises exponentially, and the voltage through the inductor decays exponentially. Okay. Now, after energizing this inductor, if you disconnect it from the battery and you connect it through the resistor here, the current will decay exponentially. So it will be the initial current exponential minus t over tau, and tau is L over R So this is how it behaves. So the current will decay exponentially. The voltage through the resistor will also decay exponentially, and the voltage through the inductor will rise exponentially from minus epsilon to 0. Okay, so this is what we have done last time, and we did some circuits. Okay, and before I move, I wanted to do one more problem. I wanted to do this one. Okay, so here, this is not an inductor, it's a coaxial cable. The coaxial cables are often connected electrical devices such as the video system. So you have a wire inside and the shielding outside, and the current flows through the wire inside the coaxial cable. So we can model a long coaxial cable as a thin cylindrical conducting shell. So this is the shell here, okay, and of radius B, concentric with a solid cylinder of radius A. Okay, so here this is a radius A, and between them there is an insulator. So the insulator should not conduct any current. The conductor carries the same current I in opposite direction. So here the current I flows through the conductor. So this is the conductor here, and it also flows back through the shielding of the coaxial cable. And the question here is calculate the inductance L of a length L of this cable. Okay, so now in order to calculate we can use the fact that we've seen that if for any device the flux, okay, the flux, the inductor is the flux linkage. So in this case it's Phi, or the flux divided by the current I. Okay, and so we need to determine what is the flux through here. So we want to determine it, calculate the inductance. Okay, so we're going to determine the flux in this case. So when you have a current flowing here, it will induce a B field, and B, we've seen that it's equal to mu 0 I divided by 2 pi r. And this is what we have seen from the magnetic field that is induced by a wire conducting current I. All right, so we need to determine the flux, and we know the flux in this case is the integral of B dotted with the A. Okay, so so let me try to determine it element by element. So let me take this element here, okay, and determine the flux through it. This element has a length L and has a width dr, so the area is L times dr. So let me call this d phi. It's L times dr times the magnetic field at that point, which is mu 0 I divided by 2 pi r. Okay, so this is d phi. So I'm going to plug it here. So the total flux becomes of d phi, where r goes from the radius A to B. So it becomes the integral of from A to B. Okay, so let's write this correctly. L mu 0 I divided by 2 pi. So we have 1 over r and dr. So this is the flux. Okay, since I'm interested in this, all is constant, so we can take it outside of the integral. So it becomes mu 0 L I divided by 2 pi, and we have the integral of 1 over r dr, which is log of r. So this is log of r evaluated between A and B, so it's log of B minus log of A. So this is the flux. Now I can determine the inductance, the inductance L So it's going to be mu 0 L I divided by 2 pi divided by I. So the i's will cancel, and we have log of B divided by A. Okay, so it's is there a different way of doing this? Yeah, well, I mean, so we just use the fact that the inductor is equal to the flux linkage of the element, divided by the current. So we determine the flux. In this case, we have the flux was not easy, because magnetic field is not constant. Magnetic field, as you get close to the inner wire, it increases, and it varies as mu 0 I divided by 2 pi r. So as r increases, the magnetic field decreases. So it's not constant. So that's why I had to perform the integral in order to determine the flux. Okay, and once I have the flux, I can plug it into the equation for L divided by the current, and I can find the inductance of this cable. Okay. Now, not only it has inductance, it has also capacitance. Remember, we had very similar problem when we were trying to determine a capacitor. So you can think about this as the inner plate of a capacitor. This is the outer plate of the capacitor, and we did, so it's like a cylindrical capacitor. And we did before, this is the material between this and this is an insulator. So it has a capacitance, and you can calculate the capacitance, equivalent capacitance, and you can calculate the inductance. So this coaxial cable, and if we evaluate the values, unfortunately they did not give us the values, it should be very small. The capacitance and the inductance are very small in this case. Okay, so let me go to the next topic, and now we're going to speak about the mutual inductance, and that's why I want to go to presentation mode. Okay, so here we have two coils, coil 1 and coil 2, okay, and so we have a current flowing through coil 1, and the current, so this coil, we are looking at the cross section of the coil, so the coil is like this, so these are the wires in the coil, okay, this is the second coil, okay, and if we have a current, the first coil has N1 terms, okay, second coil has N2 terms, okay. If we have a current flowing through this one, and if it changes, if this current changes, the flux, the magnetic flux is going to change here. When the magnetic flux changes here, it will also induce an EMF here, because the flux will be also changing through this secondary coil, okay. And this is what we usually refer as the mutual induction. So mutual induction. If we reverse the roles, same thing will happen. If I have current flowing through this one, connected to a battery, if I change the current through this one, it will induce a magnetic field that will also induce an EMF, a changing magnetic field. Changing flux will also induce an EMF in this coil. So that's why we call it mutual inductance. One affects the other. Okay? The magnetic flux caused by the current in coil 1 and passing through coil 2 is represented by phi 12. So the first subscript is the one that is causing. So here, M12, that means it's the mutual inductance due to current in coil 1 that is felt in coil 2. I mean, it's always confusing because in some books they reverse this. Okay? Now, without proof, it's just equal to the flux linkage divided by the current. Okay? In this case, the flux linkage is through coil 2. So, it's the number of terms through coil 2 times the flux that is due to current 1 that is induced in the flux, the flux change due to current 1 that is happening in coil 2. So that's why the first subscript is a cause, the second subscript is where we measure. This is the cause is current in coil 1 that we are measuring in 2. Same thing here, flux due to current in coil 1 that we are measuring in coil 2. So the flux linkage divided by the current. And the current obviously is a current that is flowing through coil 1. Okay? Now, I can determine what is the induced EMF. We said the induced EMF is minus L di dt, but in this case, instead of L, we replace L by M. So it's going to be equal minus M di dt. So this is now the EMF induced in coil 2. Okay? Yes. That is equal to minus, this is Lenz's law, the mutual inductance between the two coils times the derivative of the current with respect of time. Remember before we had this equation, we had E is equal minus L di dt. So it's the same equation except we replace L by M, okay? And now the current is caused by something else. All right? We can also do the same thing if we reverse the roles of the coils. So we can also, instead of passing a current through coil 1, we can pass a current through coil 2 and measure the EMF in coil 1, and we will find that it's equal M21, the derivative of the current. Now it's in coil 2 with respect of time. What's interesting is that we will verify in an example that M12 and M21 are equal. Okay? So the mutual inductance, they are the same. So whether you calculated it by having the current through 1 and calculated it in 2, or you do the opposite, you will find the same result. That makes our lives simpler. And the same thing also, these two equations are valid. So the EMF induced in coil 1 due to a current in coil 2 is given by the same equation. It's minus M di dt. Okay, so this is a mutual inductance. So here we're illustrating that we have, so here we have coil 1 that has N1 turns, okay, and coil 2. This is now connected to a battery, and so we induce a current through it. We can have a switch, so we can vary the current. So when we vary the current, the flux is changing here, it induces an EMF, and we can measure it with a galvanometer or with an ammeter. Okay? We can also reverse the roles. We can connect a battery to this coil now, which is coil 2, and do the same thing to coil 1, and again, the mutual inductances are going to be equal, okay? And the EMF induced in coil 2 due to current in coil 1 is given by minus M di dt, and same thing for, so this is very nice. Actually, this is very useful circuit. This is what the principle of a transformer. In a transformer, you can have your battery connected in this circuit, and you have, for example, a very large number of turns and very small number of turns, and the voltage you will get in the secondary coil is going to be much less than the voltage you get in the primary coil. And if you want to do the opposite, if you want to increase the number of the voltage, you can change the number of turns. This is what we usually call the transformer. So if you have, for example, the power line is 220 volts, and you need only 10 volts, you can use a transformer. So you have the power cord is connected to the power line, to the primary coil. So you have the high voltage, and you have a step-down transformer, so you will bring down the voltage to 10 volts because your circuit is operating on between minus 0 to 10 volts, for example. So this is the principle of the transformer. It operates on the principle of mutual inductance. So let me do this problem. This is a nice problem. This is not in your textbook. well, it's actually one of the problems, not an example in the textbook. It's one of the problems in the textbook, but I thought it's much better than the example that they have. Okay, so here we have two solenoids. Solenoid S1 has N1 terms. So this is solenoid S1, has N1 terms. Okay, with radius R1. So this is radius R1. Okay, and it's so long that its magnetic field is uniform nearly everywhere inside it and is nearly zero outside. So it's an ideal solenoid. Okay, then we have solenoid S2, has N2 turns. Okay, the radius R2 is less than R1. Oops. Okay, so this solenoid S2 has a radius R2 which is less than R1, okay, and has the same length. Okay, so one is inside the other. Now, their axes are parallel. Assume S1 carries a current I. So S1 has a current I. So let's say S1 has a current I, and let me call it I1. All right, and compute the mutual inductance characterizing the EMF induced in S2. So we want to determine the mutual inductance. So this is mutual inductance in coil 2 due to coil 1, and we said it's equal to the number of terms in 2 times the flux linkage and in 2 caused by a current in 1, divided by the current. This is the mutual inductance. So, you know what? Let me do it step by step. Okay? Now, let's first of all determine what is the magnetic field in 1. It's mu0 N1, mu0 N1 I, and let's use I. So this is mu0 N1 divided by L times I. Okay, so this is the magnetic field that is caused by this current flowing. So it's all uniform inside. Let's determine the flux through only one term of this coil, S2. So the flux through 2 caused by 1, this is only one term, is going to be just B times the area, B1 times the area, which is the area of coil 2, correct? And the flux through this is going to be this area here, so B times this area. Okay, so this becomes mu0 N1 divided by L times the current times the area of A2. Let me keep it area, it's pi r2 squared. Let me just call it A2, in order not to carry a lot of equations. Now I can write the mutual inductance in let's see here. Sorry, this is reversed. Yeah, it's correct. 1 due to 1 in coil 2. We said is equal to the flux linkage. So this flux for a single term, we multiply it by the number of terms of coil 2. So it's going to be N2 times the flux, 1, 2, okay, divided by the current. Flux linkage divided by the current. Okay, so let's replace everything. So it's mu0 N1 N2 I A2 divided by L divided by the current. The currents will cancel, and we obtain, so we obtain M12 is equal to mu0 N1 N2 times the area of coil 2 divided by L. Correct? So now let's reverse the roles. So they said, now assume, so this is A. Now assume S2 carries a current I. Compute the mutual inductance to which the EMF in S1 is proportional. and how do the results compare. So let's do, okay? So now we're going to do the opposite. So we have a current now. The current is going to be flowing through the inner coil. This is the current here. So first of all, I need to determine what is the magnetic field inside the inner coil. Magnetic field, so let me call it B2, is going to be mu 0 N2, because the number of turns is in coil 2 now, times I. So this is mu 0 N2 divided by L times I. Okay? So now we have determined the magnetic field inside this coil that is due to this current. Now we want to determine the flux in the secondary coil, in this larger coil, through a single turn. So the flux through a single turn that is due to coil 2, that is induced in 1, is going to be equal. So now the magnetic field is only inside this coil. What is the flux in this case through one turn? Is it BA1 or BA2? BA2, because there is only, so now we have only flux inside the inner coil. That's where we have the magnetic field. So when I do the flux, I cannot count this larger area I have, because there is no magnetic field through, there is zero magnetic field, assuming this coil is perfect. There is zero magnetic field here, okay? So we have to multiply by A2, not A1. This is a trick. So this is now B2 times still A2. So this is going to be mu 0 N2 L I times area of the smaller coil, A2. Now let's do M. This is due to the current in coil 2 that is induced in coil 1. So we said it's the flux linkage. So we multiply the number of turns of 2 times the flux that is due to coil 2, yes, induced in 1, divided by the current that is flowing. Okay, so what do we get? So we get mu 0. I think we made a mistake. Sorry, we have to multiply by N1 here. The number of turns is N1. The number of turns. We did the flux through one single loop, so we have to multiply by N1. So this is N1. Okay, so it will become mu 0 N1 N2, okay, I A2 divided by L times I. The I's will cancel and we obtain, this is going to be mu 0 N1 N2, and so this is A2 here, and it's still A2 here divided by L. Same value. Yes?
Because the radius was technically as the outer solenoid. So what did you take?
Why did I take this area here? Okay. Now, the current is flowing through the inner coil. The magnetic field is only in this here. So, if I want to determine the flux through this outer coil, I multiply the magnetic field by the area in which there is magnetic field. This here and here, there is no magnetic field, 0. So I multiply the magnetic field here times the area of this loop. And here and here, there is 0 magnetic field. That's why I use a smaller area. Okay, when you have a current flowing through this inner coil, we said in a perfect solenoid, the magnetic field is uniform inside it and is 0 outside. Now, when we were doing the other way, when we have the current flowing through this one, the magnetic field was through this whole thing. But we are determining the flux through this one. So we have to multiply also by the area A2. So you can say the mutual inductance is given by this equation. Make sure that this area is the smaller of the two. So here it's A2 and here it's A2. Okay, so you can see that M12 is equal M21. And it's equal to what we call the mutual inductance. واضح؟ So the idea is, first of all, determine the magnetic field due to one coil. Then try to determine what's the flux through the other coil in one term. Okay, once you determine the flux through the other coil, you use the general equation that the mutual inductance is equal to the flux linkage, which is the number of terms times the flux, divided by the current from the other coil. So I know it's a little bit confusing, but notice here 1, 2, 1, 2, 1 here, the current is 1, and the only one that has a different subscript is the number of terms. Here, N21, so this is a flux 21, I2, okay, and you have N1. So if you try to remember, but I think the best thing is to think through it and do the examples. Clear? Is the mutual inductance clear? Okay, let's solve problems then. Okay, so let's go to Kahoot. All right. Yes? Yeah, okay, inshallah. And if I put the solutions, nobody will come to the class. So, okay, yes. And that's why I want you to see the solution in class and understand them in class. So let's do, okay, play. Yes, let's join and solve some problems. This is not a difficult chapter. Okay, 356 795. Please, everybody join and work in groups. Everybody join, but work in groups, please. I want you to discuss these things. So let me start the first problem while you're joining. Okay, so the first problem, 1 minute and a half. This is an easy problem, a warm-up problem. Let me, so everybody join. All right, so let me. Well, let me make it 2 minutes, since it's the first problem. Yes. البن 356795 356795. Okay, so while you're working on this, عبد الله العطار عالية عالية خفيفة. Okay, I assume everybody is done, so let me start it out. Okay, so let's start. Okay, good. 14, all right? So here, a coil telephone forms a spiral of 70 turns and a diameter of 1.3 centimeter and unstretched length of 60. Determine the inductance. Well, so remember, the inductance is the flux linkage. So it's N times phi divided by the current I. Okay, and the flux through a solenoid is known. It's B times the area. So this is N. B times the area, mu 0, N I, this is the B, times the area, A, which is pi r squared, time divided by I. So this will cancel, and you obtain, this is mu 0, N squared times the area, N divided by L, sorry, so this is mu 0, N, small n, N squared divided by L, times pi r squared, okay? And when you do that, so you get 1.36 microhenries. Next problem. Okay, 2 minutes for this one. Everybody sign. Discuss it. Okay, done? Raise your hand if you're done. Aha, this is not it's not difficult. I'll give you another 15 seconds, 20 seconds. Okay, so choose between A, B, C, or D. I'll start. Okay, good. Well, 22 are correct and very good. All right, so let's actually. So here we have an EMF of 24 millivolts is induced in a 500 turn coil when the current is changing. So we have the 10 amps per second. What is the magnetic flux through each turn of the coil at an instant when the current is 4 amps? So we have a rate of current change and we have a current. Okay, so first of all, since we have an EMF, we know the induced EMF is minus L di dt. Okay, since they gave magnitude here, so let me use absolute value here, and so let me take this here. Okay, what is L? L is the flux linkage. L is the flux linkage, which is N times the flux divided by the current. So we plug it into here, so we obtain the EMF is N times the flux divided by I times the derivative of I with respect of time. Okay, and now I can get the flux. So the flux is just equal the EMF times I divided by N divide the I dt. So I have everything. 24 10 minus 3. The current is 4 amps. N is 500, and the derivative is 10 amp. The derivative of the current with respect of, and you get the flux. You get it is equal 19.2 microwebers, I think, not Tesla. So this should be microwebers. Okay, next problem. So 5. All right. Evaluate this at 1 second. So answer the question and evaluate the self-induced EMF at 1 second. So you're going to get the equation and then determine it at 1 second. So I'll give you 1 minute and a half for this one. يلا شباب يلا. I want to see discussions. Discuss. Raise your hand if you finish. Okay. Yalla, everybody should be. It's not a difficult one. I'll give you 15 more seconds. Okay, so choose between A, B, C, or D. Okay, I know it will be the. All right, let's see. 10 seconds. Oh, good. 17. Okay, versus 9. Okay, so let's look at this one. Okay, so here we have a 10 millihenry inductor carries a current that is given by a sinusoidal function I max sine omega t. I max is 5 amps and the frequency f, which is omega over 2 pi, is 60 hertz. So omega is 120 pi radians per second. Okay, what is the self-induced EMF? We have an equation that says this is minus L di dt. Okay, so we have the current, so this is minus L, the derivative with respect of time of I max sine omega t. Okay, so what's the derivative of sine? Derivative of sine is cosine, and so this is going to be equal minus L I max omega cosine omega t. Correct? So this is the general equation, and we are asked, so this is, let me write it, so this is 10 to the minus 3 times I max, which is 5, times 120 pi, this is omega, cosine 120 pi times t. All right, so this is the induced EMF with a minus. Okay, so now if you calculate it for t is equal to 1 second, what is cosine 120 pi? Cosine 120 pi what? جماعة, cosine 120 pi is what? What's cosine 2 pi? 1. Cosine 120 pi is also 1, so it's actually minus. So it is minus, it's minus 18.8 volt. So this is actually, in the Kahoot it was incorrect, it's minus 18.8 volts. Okay? All right, next question. Okay, so here just determine what is the EMF between 0 and 4 milliseconds. Between 0 and 4 milliseconds, 1 minute and a half. So this is very similar to the previous one, actually. So determine the EMF between 0 and 4 milliseconds. Want to magnify it? Who finished? Majority finished. So, okay, we'll start. Choose between A, B, C, or D, and I will start. We'll have 10 seconds. 5. Okay, 15. Okay, I expected better than this because we just solved we used the equation in the previous problem. Okay, so here we have a current in a 4 millihenry inductor varies in time as shown in the figure. So this is the variation of current with respect of time. Construct a graph of the self-induced EMF across the inductor over time between t to 12 milliseconds. Well, we don't want to do for the whole thing. So the equation is minus L di dt. So di dt is a slope. Okay, so what is the slope here? Okay, so this slope minus L. So let's call this I2, I1, T2, and T1. So the slope is going to be I2 minus I1 divided by T2 minus T1. And when you evaluate this, so this is a negative slope. Since it's a negative slope, negative times negative, you get positive. Okay, and so it will be L. So it's going to be 2 milliamps, 2 10 minus 3 divided by 4 milliseconds, 4 10 minus 3. Okay, and when you do that, you find that it's going to be equal to 2 millivolts, and you can do the same thing for the other intervals, and you can plot the whole EMF. So you can see the EMF in this part, it's positive because the slope is negative, and this part the EMF is negative because the slope is positive. Here the slope is 0, so there is no variation of current, so hence there is no induced EMF, and in this part the slope is negative, so the EMF is positive. Next problem. Okay, 2 minutes for this one, just question A. Well, actually this is 1.5 minutes, 1.5 minutes. This is easy. Let me magnify it. So 500 turn solenoid has a radius of 8 millimeter and a length of 14 centimeter. What is its inductance? If the solenoid is connected in series with 2.5 ohm resistor and a battery, what is the time constant of the circuit? If you forget the equation for inductance, for inductor always see the flux linkage divided by the current. Finished? Who finished? Raise your hand. Almost everybody. Okay, so we'll start. Okay, excellent. 20 versus 7. All right, so let me go and see it. Okay, so here the solenoid has 500 turns, okay, and has a radius of 8 millimeter and a length of 14 centimeter. What is the inductance? Either you memorize, if you have a weak memory, like myself, I do the flux linkage divided by the current. So that's N. The flux linkage is the magnetic field times, so it's mu 0, small n, which is N divided by L, I, times the area, divided by the current. Current will simplify, and you obtain mu 0, N squared, divided by L times the area, which is pi r squared. Remember, sometimes the area may be rectangular, so don't always use pi r squared. All right. So this is L, and it says the solenoid is connected in series with an inductor. So we have an R, L, and you have a battery. Okay. So here they asked for the time constant. So the time constant we said is L over R, but we could have asked for what is the current, for example, at 1 second. If the after we close the switch. So this is epsilon over R 1 minus T over tau, which is RL RT divided by L. So in this case, if you're giving time, you can determine what is the current. But they did not give us the battery voltage. But let's assume they give us the battery voltage. But the time constant is this one, L over R. Clear? واضح. Okay, next problem. All right. So here I want to go to the, I will skip this one. I will go to the next one. I'd like to do the interesting one about mutual inductance. Skip, skip, next. No, I want not this one. Yeah, next, next. Okay, let's do this one. So an EMF, all right, we can do this one. Actually, no, let me skip this one. This is simple. I want to go to the last one. Somebody answered immediately. Wow. Okay, this one. 3 minutes for this one. Some of you, you're ready before. Okay, so just answer question A. So now we will determine whether you understand mutual inductance or not. So we have two solenoids A and B, spaced close to each other, sharing the same cylindrical axis. One has 400 and the other 700 turns. A current of 3.5 amps is in solenoid A, produces a flux of 300 microwebers through each turn of A and 90 microwebers through each turn of B. So we have the flux in A and B due to the current in A. Calculate the mutual inductance of the two solenoid, the inductance of solenoid A, and the EMF that is induced when the current in A changes at 0.5 amps per second. Nice problem. So you have the flux through one turn. Remember, mutual inductance is the flux linkage divided by the current. Flux linkage, number of turns times the flux divided by the current, that will give you the mutual inductance. The inductance is also flux linkage, but it's different flux. It's flux in the same coil. Okay, ready? Raise your hand if you're ready. I need 2 minutes to do this one at least. Huh? Okay, for the sake of time, because I need to solve it also. So choose between A, B, C, and D, and I will start. Well, that's very good. 17. Good, good. Okay, so let's go over this, and I want to do it step by step. Okay. So here, let me draw the situation. We have coil A that has 400 turns. This is NA, and coil B that has 700 turns, okay, respectively. The current in A is 3.5 amps. So this is a current in A, 3.5 amps, okay, in a solenoid, and it produces 300 microwebers through each turn of A. So, and 90 microwebers through each turn of B. Calculate the mutual inductance. All right, we know the mutual inductance due to coil A, okay, in coil B is equal to the flux linkage, which is the number of turns in B, the flux due to A that is induced in B divided by the current, and this current is in A, okay. So this is equal, and B is 700, so 700 times the flux that is induced in A, induced by A through B, which is 90, 90, 10 to the minus 6, divided by the current, in this case 3.5 amps. Okay, so you find that this is equal to 18 millihenries. 18 millihenries. Okay, now the next question, what is the inductance in A? The inductance in A is the flux linkage, which is the number of turns in A, times the flux in A, divided by the current in A. So that will be 300, the number of turns is 400 in A. The flux in A is 300 microwebers, 300 10 to the minus 6, divided by the current, which is 3.5 amps. And when you do that, you find that this is equal to 34.3 millihenries, 34.3 millihenries. The next question, okay, what is the EMF induced in B when the current in A changes at a rate of 0.5 amps per second? We use E is equal minus M di dt. Okay, so this is the induced in coil B due to current in A. Okay, and since we have the mutual inductance, so this is 18 minus 18 10 to the minus 3 times the derivative of the current, which is the change of, so 5 amps per second. Okay, and we get the induced EMF. And since here they did not indicate directions, they must be meaning the magnitude. So you can get the EMF. So this is how you can solve problems with mutual inductance. I hope this is clear. With practice, it will become more clear. See you tomorrow. We'll start the next chapter.